Good morning, dear colleagues. Do you hear me? Is it okay?
Yes, everything is fine.
Okay. Here you can see the title of my presentation and here the outline of my talk. First of all, I'll present the general concepts of my talk, of our research that we are conducting in the Institute of Applied Physics in Nizhny Novgorod, Russia. And after that, I'll give a brief discussion about using glasses for our nonlinear microresonators, and after that I'll present some results concerning nonlinear Kerr and Raman effects in silica glass microresonators in nonlinear, and after that nonlinear Raman effects in chalcogenide glass microresonators, and after that I'll tell you about our achievements in the field of lasing in tellurite glass microspheres. First of all, it is well known that the spring gallery modular resonators with high Q factors and a small mode volume providing efficient light-matter interaction are very attractive photonic elements for obtaining optical frequency combs for different applications, as well as creating optical filters, switches, microanalysis sensors, and other miniature optoelectronic devices. Microlasers in the range of about 2 microns are potentially interesting for extensive application in remote chemical sensing, biomedicine, and atmosphere monitoring, and so on. In the Institute of Applied Physics, we created and developed a fairly universal experimental setup for investigation of nonlinear optical and laser effects in resonators in microspheres based on different glasses. We developed theoretical models to describe the observed effects, and we obtained a set of experimental and numerical results, and our results are in a good agreement to each other. And here I'll tell you about using glasses for our microresonators. It is well known that silica glass is a commonly used material for microresonators. Just very common, and such resonators can be made from standard telecom fibers. They have zero dispersion wavelength near 1.3 microns. Their nonlinear refractive index is given here, but they are not very transparent in the range beyond 2 microns. In contrast, chalcogenide glasses are very attractive and promising for using in the mid-infrared region. You can see that chalcogenide glasses have huge Kerr nonlinearities, and Raman nonlinearities is very high too. That 2-3 orders of magnitude higher than for silica glasses. Chalcogenide glasses can be used for producing microresonators, and currently should be noted that such glasses are commercially available. Fibers based on these glasses can be available. So you can see that very good mid-infrared transparency, and they have very low phonon energy, which can be used for laser applications. And tellurite glasses, they are mediate between silica and chalcogenide. They have a high nonlinearity, but transparency up to 5 microns, and not very low and not very high phonon energy, and they have good properties for using them in laser devices. We used in our experiments and our numerical simulation all three types of glasses. And first results concerning Kerr and Raman effects in silica microspheres. Here you can see the general scheme that we used for our experiments for all glasses. They are very similar. It consists of here it consists of a silica microsphere with a diameter of about 170 microns. We optimized the diameter to obtain zero dispersion wavelength at 1.55 microns. The microsphere was made of a standard single-mode telecommunication fiber using the purposely designed programs for the Fujikura fiber splicer. The microsphere was punched by a CD laser, widely tunable in the C-band. We used pure Photonics laser with 60 nanometer tunability and 10 kilohertz line widths. Coupling of pumped light and outcoupling of the generated light was arranged with a fiber tape also made from a standard fiber. The nonlinear dynamics of intracavity fields leading to optical frequency comp generation was described in the framework of the Lefebvre equations. Here and further, we used this model. We use homemade software based on the split-step Fourier methods. And as concerning this research, these figures, we studied Kerr and Raman nonlinear effects in the microsphere punched near the zero dispersion wavelength. In the modeling, to reveal the Raman impact on the optical frequency comp shape for different dispersion regimes, we modeled this equation with allowance for Raman response by setting the Raman contribution and purposely without Raman effect. Here you can see the experimental spectra, and here you can see the simulated with taking into account Raman effects and without taking into account Raman effects. You can see that Stokes component noted as S corresponds to Raman effects, and AS anti-Stokes components corresponds to four-wave mixing between pump and Stokes frequency comps. Here you can see the regime when the pump in the normal dispersion range. You can see only Raman generation without anti-Stokes components, and here you can see the phase match conditions. There is no phase matching in the normal dispersion range. We can state that this is only due to Raman effects. When we set Raman contribution is equal to 0, there is no Raman generation. Then the pump wavelength was near zero dispersion length. We can see this matching condition and experimental Raman Stokes and anti-Stokes components. They are verified in simulation, and when there is no Raman effects, there is no comps. After that, then pump wavelength was in small anomalous dispersion range. We can see very broad optical frequency comp and different components corresponds to Kerr and Raman effects. Here we can see that nearest to the pump peaks corresponds to Raman effects due to the do not vanish when we switched on Raman effects. And then the pump was in anomalous dispersion range with slightly higher value. We can see the the optical frequency comp with some changes. So in this study, we demonstrated the Kerr and Raman optical frequency comp in silicon brass wave pumped near zero dispersion wavelengths. The second results also concerns effects in silica microresonators. Here we obtained experimentally Raman-assisted nested optical frequency comp in two different mode families with soliton-like spectral envelopes for each mode family in a silica microsphere. The experimental scheme is very similar. We also used the microsphere with 170 micron diameter here. And here you can see the experimental results. We report the regime, then the pump wavelength, as you can see, without optical frequency component by the pump is in the normal dispersion range, and Raman-assisted optical frequency comp are generated in the anomalous dispersion region. We approximate the envelopes for the experimental parts of the spectral belonging to two different mode families by solidonic-like shape. And here you can see the transformer limited pulses in the time domain, and they correspond to the solidonic-like pulses with such durations. And after that, we calculated dispersion for TE and TM modes using the characteristic equations originating from the Maxwell equations. We compared the experimental frequencies of spectral harmonic of the Raman assistant of this with the calculated modes, and found that comp with a larger bandwidth range corresponds to TE modes, and with a low width corresponds to TM modes. So this was the experimental results concerning silica microsphere, and after that let's speak about nonlinear Raman effects in chalcogenide glass microspheres. This is the next stage of our results. To date, multi-mode Raman lacing in chalcogenide microresonators was obtained in a few works, about 2 or maybe 3 without our results. Potentially, Raman generation in chalcogenide microspheres can be obtained in the mid-infrared range, which is inaccessible, for example, for silica microresonators. However, even in the telecommunication range, chalcogenide microspheres are made of arsenic sulfide glass can have certain advantages. It is possible to obtain Raman lacing in the L band with a C band pump, which may be potent for some applications. A chalcogenide glass microsphere was fabricated in air atmosphere from arsenic sulfide based commercially available fiber. The protective polymer coating was removed, and after that a piece of chalcogenide fiber was softened and stretched to form a taper with a minimum diameter of about 20 microns using a homemade resistive microheating. Then the chalcogenide taper was divided into parts, and next the end of the tapered arsenic sulfide fiber was inserted vertically to the microheater, and after that a microsphere was formed under the influence of surface tension forces. The process was monitored by an optical microscope, and the heat power could be adjusted in real time. The microsphere diameter controlled by changing the heat duration. We produced samples with different diameters, but Raman lacing was obtained in a microsphere with diameter of about 34 microns. The experiments of Raman lacing in produced microsphere were performed according to this scheme. The microsphere was pumped by the same tunable CV laser as for silica microresonators. We used a silica fiber taper. Then the pump power exceed over the threshold was not very high. We attained single motor Raman lacing tunable in the L band and in the U band. Here you can see the experimental results. And more than 50 nanometers wavelengths tunability was achieved solely by a pump wavelength tuning in glass microsphere. Here you can see the numerical simulation results based on the Latvia equations, which agree very well with the experiment. Here experiment, here numerical, and they are in a very good agreement. Further, then the pump power significantly exceeded the threshold for Raman lacing. Raman lacing became multi-mode, and different families of whispering gallery modes were excited. Moreover, cascade processes were absorbed. In cascade processes under the action of continuous wave pumping. Initially, the first order Raman radiation is generated, which serves as the pump for second order Raman radiation. And then the second order Raman radiation is a pump for the third order Raman radiation, and so on. As our optical spectrum analyzer have a limitation for spectral range beyond 1.7 microns. To register these spectra, we use a homemade scheme based on monochromator and amplified detector. So we obtained for order Raman lacing with pumping at 1.57 microns. The first order of Raman lacing was at 1.67 microns. The second order was at 1.76 microns. The third order Raman, laser was at 1.88 microns, and the fourth Raman order was at 2.01 micron. And let's go further, and let's speak about tellurite glass microspheres. In tellurite glass microresonators, we studied laser effects. And first,
sorry, you have 3 minutes.
Okay. We considered thulium doped microlasers. We proposed a numerical model, and we developed the corresponding approach. We proposed an original method based on solving a system of algebraic equations with taking into account all the games in the active bands, and we show that it is possible to obtain laser generation at free laser transitions in thulium-doped matrices. And after that, we investigated the possibility, theoretically investigated the possibility of laser generation in thulium-doped microsphere. We demonstrate the possibility of generating a single color lacing, two-color lacing, and free color lacing, depending on parameters of the system. Our results are in agreement with experiments by other research teams. And after that, we performed our experimental studies in thulium-doped tellurite microspheres using in-band pump. This is a simplified scheme. We used the same pump and obtained generation 2 microns. Here you can see the experimental results in our homemade microsphere. And after that, we started laser generation in erbium-doped tellurite microsphere. We also developed numerical module and obtained very interesting results concerning that generation can observed in C band and in L band, and we found that depending on Q factors, depending the wavelength generated can jump when we switch on pumps. And here you can see the last results, our experimental results in erbium-doped microsphere, depending on setting, single mode lacing and multi-mode lacing in the C band and in L band was attained in homemade microsphere by changing the parameters of the system, mainly the distance between the microsphere and the fiber taper and the pump power. We obtained different regimes of lasing. And here the summary of my presentation. Thank you for your attention.
Thank you, Elena, for your interesting presentation.